Hello everyone and welcome to Next webinar series. This is Aparna Deshmukh and I'm Technical Director with Next and I will be your moderator for today's session. So we are excited to dive into our today's webinar titled Efficient Utilization of Non-Compliant Aggregate for Resilient Concrete through Chemical Admixtures. So a PDF of this presentation can be found in the handout box. You can use a PDF to follow the presentation and take notes. You may also use the question box to ask questions during the webinar, and a speaker will address them at the end of the presentation. So for continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PD Edge. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the next webinar series. Let's begin with a brief description of today's webinar. This presentation will provide an insightful overview of methods for using non-compliant aggregates in concrete while maintaining structural integrity, focusing on chemical admixtures, ASR mitigation, enhancing weak aggregates, and evaluating non-compliant sands. It will discuss the outcomes of the research study that will offer standardized, practice-ready guidance for designing resilient concrete mixtures that effectively utilize non-compliant aggregates. So our learning objectives for this webinar are as shown on the screen. Now let's welcome and introduce our today's speaker, Dr. Armin Amirkhanian. P is an assistant professor at the University of Alabama with over a decade of experience in applied research on civil engineering materials and concrete pavements. He is actively involved in the American Concrete Institute as a voting member of several committees and he is also the secretary treasurer of the International Society for Concrete Pavements. Dr. Amir Khanian has led research projects for various DOTs and agencies and is a registered engineer in the 3 states. So now Armin, welcome to the next webinar series and let's listen to your presentation.
Thank you. Yeah, I'm Armin. I'm going to talk about some non-compliant aggregates. And I know this is a big thing because, we're engineers, we like following specifications. And if our aggregate doesn't follow the specification, well, we're going to have a problem with the project. And I want to start off by saying, this work was pretty extensive and could not have done it without significant, help and support, not only from ACI Next, but also from the PhD student who's actually getting his second PhD, and a huge amount of undergrad researchers who have helped me over the almost 2 years on this project. And so we're going to kind of go over what the overall project was, how we're going to talk about some of the very specific results from the ASR chemical durability portions as well as the gradation one, and then kind of summarize some stuff here. And so when we look at the project, we kind of had 5 objectives, and that was to utilize non-compliant aggregates that were non-compliant either because they had chemical contamination, they were known ASR active, they had soundness issues, or the gradation was falling outside of the C33 bounds. And I'll just point out that that was for the sands, not the coarse aggregate. And then finally, kind of the 5th objective was, okay, after you get kind of the answers, or at least ideas of answers, how are you going to make recommendations either for code changes or just general practice? So this presentation, because we don't have a lot of time, is going to focus on the chemical, ASR, and gradation aspects. And even with that, it's going to I won't be able to present a lot of the results we have just because we don't have a lot of time here. So we'll get started with ASR. I think probably a lot of you know what ASR is. And so I summarized it in a single sentence. It's a reaction between alkalis and reactive aggregates. Ooh. This is why I get paid the big bucks. But the really important part is it needs water to go. If there's no water, we don't have a reaction. And several mitigation strategies over the years have kind of focused on that by essentially like, okay, we'll kind of protect the surface of our concrete so water doesn't continually get into it. So that's a good avenue for mitigation. Not always applicable for every type of project. And the reason we don't want it, when it forms this gel, the gel is expansive, causes a lot of internal stress, and our structure starts cracking a lot, which is not good. Now, when we look at the current state of practice, ASTM C1778 has some flowcharts and tables and stuff to really provide some information to the engineer to kind of think about what they should do depending on the aggregates they're trying to use in their locality. A NCHRP, which is National Cooperative Highway Research Program, just finished 10-103, which was looking at offering improvements to that ASTM guide. And there's been a lot of work in that area over the past decade, and a great summary presentation was given at the fall ACI convention in Boston. I believe those links should translate to the PDF you can download, so you can click that actual link there and that takes you to the presentation. But in general, if we're trying to mitigate ASR with state of practice techniques, we're going to utilize SCMs, and we're going to try and minimize that moisture. We might seal the concrete after construction. We might use an integral waterproofing agent, or we just might try and prevent use of suspected ASR active aggregate in conditions where the concrete would get moisture exposure. Now, jumping back to that SCMs, I'd say almost all concrete. A lot of concrete made nowadays already has SCMs, so that's great. So we're either directly or indirectly mitigating a lot of this. Now, in the past, we've shown success, or there has been success shown with lithium nitrate admixtures. In a sense, it kind of poisons that gel from forming. It doesn't allow it to form in the way that is expansive. And those have been shown to work usually. There are some cases where it may not. However, lithium is pretty darn expensive right now, especially with all the electric vehicles, electric everything. And so it's my understanding, I'm not in industry, but it's my understanding from talking to people that lithium nitrate is not really a practical solution to ASR active aggregate sources. And then I added this thing at the bottom, alkoxysilane. It was shown way back 30, 40 years ago as a potential admixture to mitigate ASR. And when you follow that research, it never really progressed beyond just kind of a few studies, which was kind of interesting. So that, coupled with some other recent research, led us to think about, all right, we're going to use SCMs, we're going to minimize moisture, but what else can we do? And we're going to dial in on this, let's prevent water from touching the aggregates. If the water's not there, the reaction can't go. So in this study, what we did, we took known non-reactive aggregates and known reactive aggregates, mixed them, made concrete samples, did 4 different ASR tests, And what we did with the aggregates was nothing as one test case. We coated the aggregates themselves prior to mixing with that silane compound. Okay, so what we did is almost coat or protect the concrete from the inside out. Now, this is different than an integral waterproofing agent because the integral waterproofing agent essentially goes into the porosity of your hydrated concrete and kind of seals it off, which is good, you know, because we're still preventing water. But what we thought was, hey, what if you had a whole stockpile of this aggregate, known reactive aggregate, and you're really desperate and really wanted to make some concrete? Can we just kind of, as we're batching that sand, just kind of spray some of the silane on it as it's going into the mixer and see what happens? And so that's kind of what we did there. And then a third test case was, all right, we made the concrete doing nothing, just as is with known reactive aggregates. Let's coat the outside and see how those specimens do in these 4 ASR tests. So the idea revolves around not poisoning the gel structure from forming, not using SCMs to reduce the alkali loading, but actually just trying to prevent the water from touching things it doesn't need to be touching. And so what is this coating? Well, we used a commercially available alkoxysilane compound. I say commercially available because we have silane sealers available from numerous manufacturers. And so we selected one, we applied it at the manufacturer's recommended dosage. Now, the manufacturer has no recommendation for how you coat sand. And so what we did with that, we took the gradation of the sand we used, made a few assumptions, and estimated the surface area of that sand, and then used the dosage recommendation from the manufacturer and applied that amount of sealer to the sand material as we mixed it up. And it worked pretty well. We could see that there was very little, for lack of a better word, drippage of excess sealer. So it seemed like that we kind of got it pretty close to just coating the aggregate, but not having a bunch of extra. So that's kind of what we were doing. And we did a lot of testing. We had numerous known reactive aggregate sources that we tested, but for sake of this presentation, we're going to focus on kind of comparing a essentially limestone to one of the most notorious, I guess you could say, reactive sands, the Job sand from Texas, which has decades of test data associated with it. So we wanted to make sure we could, we were running our tests and got similar results, that have been obtained in, past decades, but also we know it's reactive. And we purposely designed our mixes that had no SCMs because we really wanted the worst case scenario with our test cases here. And then for the ASTM test, we followed like the actual mix designs that were outlined in those. And I'll briefly go over those as we go through each set of results. Now, the first test we did is actually not an ASTM test. They've been trying to get this to be an ASTM test. There are some challenges, but basically we have a test from the literature, the research, that is a 5-hour ASR test. It's kind of misleading because you have to let the mortar bar cure for 2 days. So you could call it a 3-day test. But essentially, you're going to make mortar bars very similar to how you make them in the 2-week ASR mortar bar test. But after day 2, you're going to take that mortar bar and stick it in an autoclave. And if you're not familiar with an autoclave, it's basically something that's used most often to sterilize medical equipment because it gets really hot and puts it under pressure. So it's a glorified, pressure cooker, Instapot, but it's pretty big, so we can fit our concrete specimens in there. And what we do is put it in there at 130 degrees Celsius and 0.3 megapascals pressure, I believe, for 5 hours to accelerate the chemistry of that reaction enough to see if anything happens. And this is my personal opinion, others who have done this test have other opinions. My personal opinion is this is a yes-no test. I am going to plot some of the data and show you like the actual expansion values and everything. But again, in my opinion, it's really like binary. Did it pass some threshold or not? We can't really, say, oh, it's this much more reactive. And I'll explain why when we look at the data. Because the overall, or I guess the initial intent of this test was originally establishing rapid military construction in parts of the world that have unknown reactivities of sands. And I want to shout out to Dr. Wood, who did a ton of research, including her whole dissertation on this very topic of using an autoclave ASR test. She's now at the U.S. Army Corps of Engineers in Vicksburg. And I'm actually using the exact same autoclave she is because I took over the lab she was in right after she graduated from UA. So all this testing is very, very similar to that publication there. So results. We have on the left, right here, our ASR active, our Job sand. Both tested at 3 days old and at 28 days old. The letter E is our internal representation for Job sand. It's sample E. And then the dash D means that only the surface of that mortar bar was coated with the silane. And the 90 or the 60 indicates that there's no surface coating, but the aggregates were coated prior to mixing. And what we see here is quite astounding. We have a known reactive aggregate. As we see here, it has tremendous expansion. Surface coating it didn't really do anything. But man, you coat those aggregates, and it's almost as if it's not Job sand anymore. That's kind of crazy. And then we go to 28 days and we see a similar trend. The aggregate as is still highly expansive, similar with the surface coating, but then we coat the aggregates and then don't even have to do anything to the surface of the concrete, or in this case, mortar. And we see it's not reactive. Wow. On the right, we have the lab sand, which is limestone. And this is going to highlight why I say it's a yes-no test. So this limestone sand, according to this autoclave test, shows some expansion that's indicating it's reactive at 3 days. But at 28 days, as expected, limestone is not forming ASR gel. Now, we could say it's an alkali carbonate reaction, which is also possible. But we don't have reason to believe that happened in this case. But the big thing about this autoclave test is that at early ages, so if we're testing when the mortar is only 3 days old, it's not very strong. It still has, because of the prescribed mix, a fair amount of water in it. And we're heating it up to 130 degrees Celsius and inducing a tremendous thermal strain and stress on that specimen. And it's my, again, personal opinion that we are actually causing expansion due to cracking in some cases due to the thermal shock rather than actually measuring ASR expansion. Waiting to 28 days to do the same test, the concrete is a lot more resilient to that thermal behavior, and I think we get a better reading. Now, if we're thinking military applications, yeah, they're not going to wait 28 days to go build something out in another country trying to figure out if the sand is reactive. so maybe that's not the best recommendation. But for DOT work, where we have, usually months to do stuff, it's maybe a little more plausible. But regardless of that, we see that coating the aggregates had a beneficial effect on our known reactive sands. Woohoo! That's pretty awesome. So the question is, did this hold up in the remaining 3 ASR tests? Well, let's see. So the next test is the 2-week mortar bar test, ASTM C1260. This is a test that's not above the boiling point of water or under high pressure. It's only at 80 degrees Celsius in an aggressive alkali solution for 14 days. And you measure expansion over time. And we'll jump to the results here. Again, our Job sand, our known reactive sand, is on the left. And here we were looking at different coating thicknesses and everything as part of the study. But the square, the black square, is nothing is done to the sand. It's just used as is. The red circle, green triangle, right here, these are surface coated samples at different surface coating thicknesses. And then the remaining 3 right here, and then this one, are just the aggregate being coated. Now, what we see here is even coating the aggregate, which in the autoclave test made it look like it was great, it still shows up, according to C1260, as suspected strongly reactive, but less suspected strongly reactive than the suspected strongly reactive of not doing anything. Okay, so maybe this is not the super magic bullet, but it had a profound impact on the behavior of this known reactive sand. And then we look over here at our limestone sand, and we're like, what? Hold on, how is limestone suspected reactive? Well, we did an insoluble residue test on this limestone we had in our lab. It actually has about 5 to 7% silica in it, which I'm assuming if we do a more thorough petrographic analysis, we would probably see that silica is actually a reactive form of silica, because we're seeing some reactivity from a limestone source. So that was kind of a surprise. But even though it shows up as being strongly suspected reactive, when we coat, we see a decrease. Now, the 2-week mortar bar test is okay, but it's only mortar, and it's at 80 degrees Celsius in a strongly alkali solution. It's possible that the silane coating on the aggregates is not stable in that environment, and that environment doesn't really reflect real-world conditions. So we went to AASHTO, T380. Now, this doesn't, again, necessarily reflect super real-world conditions, because we're still at 60 degrees Celsius, but it is less aggressive to the coating, to the material that we're putting in there, and we do run it for a longer period of time to see what we might get. And the results here, we see kind of that same trend where if we do nothing, our Job sand is very highly reactive. I forgot AASHTO adds a 4th category. Surface coating it is okay, that has some effect, but coating the aggregates is a significant effect on the expansion behavior of the specimens. Now, it still has not made this particular source of aggregate usable. I would never design anything, even with something like this. However, it is showing that if we have maybe a marginal aggregate that we think is reactive, or even historically has shown some reactivity, we can significantly reduce that potential by just coating the aggregates. And when we again look at our lab sand, which through the course of the study we realized is not as inert as we thought it was, we still see that we can minimize some of that reactivity. And then, because we have to have a gold standard here, we have the 1293 test that we're doing. This is a minimum 1-year test. Can be run up to 2 years. Honestly, you could let it run for multiple years after that. There's nothing that says you can't. Much more appropriate environmentally to simulate like conditions. It's only 38 degrees Celsius, and our research is still ongoing because this is a really long test. But I have the results up to date so that I can show you. And here's where we get into some crazy stuff. So on the left is our Job sand. This is what is defined as reactive, non-reactive in terms of expansion. And we see, this is crazy, when we coat the aggregates, we have made this situation so much worse than doing nothing. Or actually, when we coat the surface, it made it a lot better, because water can't get to it. So what is going on here? We coated the aggregates and it made it worse. So this now is getting into something and examining the actual chemistry of how silanes behave in highly alkali environments. And when we look at the literature on this, there's essentially none, because most of these silane compounds in the realm of concrete usage are used on the surface. They're not exposed to highly alkali environments for extended periods of time or elevated temperatures. And so the chemistry of this is really not well understood at this time. However, based on the data we have and the pending petrographic analysis we have of these samples, we think we would have an answer, because while the Job sand exhibited this trend, not all of our known ASR active sands showed higher expansion compared to not doing anything. And so in the context of ASR, like a lot of people say, it's complicated. There's no single answer. But look at the effect of just coating the surface. Huge, almost non-existent expansion in the specimen, even up to and beyond 200 days. And when we look at our lab sand, we see kind of a similar thing where we add the coating on the aggregates themselves, we're seeing slightly worse performance than nothing or just coating the surface of the aggregates. So we kind of have a complicated scenario here. But in other cases with other aggregates that are known reactive but not as reactive as Job, we see that even coating the aggregates has a beneficial impact on the behavior. And so some takeaways here: we can use silane to have positive impact on reducing that ASR gel formation. We can be as, out of the box, if you want to think about it, as coating the aggregates prior to mixing. The asphalt folks sometimes do this with some of their admixtures, or they do it actually during mixing in the double drum systems that some plants have. So this is not really like unusual in the grand scheme of things. Maybe for concrete industry it is. I don't know of any ready mix plant that would be set up to just immediately implement this. But again, if we don't have good aggregate sources anywhere nearby, we're going to be needing to come up with some, solutions to that. And we can't be afraid to think outside the box here. And I did mention ASR being ASR. Well, if you've seen any ASR presentation from anyone really, you'll see that, sometimes we get conflicting results. It's a very complicated system and reaction, and it doesn't always behave in ways that we expect or would even like it to. Now, one question, and I have data, but again, trying to get through some other stuff here. Your coating aggregates, doesn't that reduce the strength of your concrete? The answer is yes, it does. However, It's not significant in most cases. And what I mean by that is, let's say you're making a structural concrete mix for a reinforced beam. You need 6,000 psi compressive strength. Well, in the lab, when we were making the ASHTO beams, because that's a concrete prism, we were getting 8,000 psi with the aggregates not being coated, and then about 7,000 psi with the aggregates being coated with the silane. So it did reduce the strength, but we still had adequate capacity or remaining capacity in the system that it was not a problem. Now, if you want to do a more probabilistic approach, sure, maybe if you increased the uncoated mixed strength a little bit more to give yourself some more safety factor for the decrease that you might have if you're coating the aggregate. And that's doable, but it does decrease the strength. The other part is cost. We're always thinking about money, and this, if any of you have used silane, and I didn't know this till we started the project, good Lord, silane's expensive. Compared to like calcium chloride accelerators. So in the realm of admixtures, it is more expensive. However, going back to if you only have certain sources available and you have critical applications, this could easily be worth the cost than the risk of having ASR damage a critical structure. So there's going to be way more data and takeaways in the final report for this project, but I just wanted to kind of summarize that for ASR. And we're going to move right along to the chemical durability. And now we're saying, we either have sand or recycled concrete fines or a combination that has chlorides, sulfates, or both, because those are common contaminants in our sands and recycled materials. And a lot of specifications kind of preclude the use of those, rightfully so, due to corrosion and sulfate attack concerns. So we took sand, and no one is just going to give us contaminated sands because no one wants to call their sand contaminated. So that was the whole thing. So we made our own. We vacuum saturated our own sand with dosages of chlorides, sulfates, and sulfates to make our own contaminated aggregate sources. And you see here the dosage or the contamination level. It's actually kind of hard to find, a typical contamination level because it's so variable. So what we did, again, going kind of to the extreme and worst case scenario, we found the highest level of chloride contamination that was reported in the literature, and that was 25 grams per liter of water got us to our aggregates being contaminated. And then the sulfates was actually even crazier. So the sulfate contamination level can go way higher than the chlorides, especially when you have recycled concrete that's being reclaimed from like slabs on grade, where the grade itself is a very high sulfate soil, or you have other sources like agricultural sources of contamination with sulfates. So the sulfate level is really high. And we're doing the same thing. We're coating the aggregates, we're coating only the surface, and we're seeing what happens. And I like this picture here because on the left we have base, where we do nothing with the silane. You see the surface is very wettable, the concrete is moist throughout, and reactions can occur. In the middle here is when we mixed the concrete and we had a coated aggregate in the mix. The surface is not coated, but just the aggregates are. And we see that has a profound impact on the wettability of that matrix. And then we looked at coating the surface, and you can see in this case, for this mix, the silane went about 3/4 of an inch in to the surface because that part's not wettable and only the interior part's wettable. So that's what we were thinking, like, okay, how are we going to use known contaminated aggregates in this? And so when we talk about chloride contamination, either with sulfates or not, just if chlorides are present, the big concern is corrosion of the reinforcing steel. And so we're like, all right, let's evaluate this. Let's purposely put chloride contaminated sand in concrete and see how it corrodes rebar. Well, there's no ASTM test for that. There's a bunch of corrosion ASTM tests, but none where you're specifically taking contaminated aggregates and trying to monitor the behavior. So we went to the literature and kind of came up with a test of our own based on a bunch of kind of almost disparate testing regimes that were developed over the years. And we have this. When we were trying to make it simple so people can replicate this very easily. It's all at room temperature, which means it will take longer. If we had done this at elevated temperature, we could see something happening sooner, but based on our experience with ASR, the temperature and the silane, we didn't feel it represented real world conditions. So room temperature, 90 days, just tap water. You could use lime water if you wanted to. We actually kind of wanted to see how, if we used plain water and we got some leaching and some of that calcium hydroxide coming out, it would increase porosity and make it even worse for the concrete sample. And we're going to measure half cell potential. That is a standard test. So the measurement is standard. It's just the sample conditioning and prep is not standardized. And very quickly, because we're running out of time here, the results. Ooh, look at this. Okay, so if you guys have done half cell potential measurements, you're trying to stay in a certain region of potential because that indicates that there's likely no corrosion occurring. On the left, we have our base mix, and base mix in this case means we are using aggregates that have no contamination. And so we have a base mix. We have base mix where the aggregates were coated with silane because we wanted to see if there's any impact. And then we have a base mix where the surface was coated. And we see that all those have 90% probability, no corrosion. Now, we add in contaminated aggregates, they're contaminated with chloride, but we haven't done anything to protect it. Just tossed it in. Boom. Our probability of corrosion shoots up as expected. But look, we coat those contaminated aggregates with the silane, and we have jumped back down to as if there was no chlorides in those aggregates. And then if we actually coat the surface of the sample, we see the same thing. Now, I want to caution, if you're not familiar with half cell potential measurements, it is, and again, in my opinion, dubious to say, like, if you look at chloride contaminated and the aggregates coated or sample coated, that, oh, look, you like cut it in half or you cut it by, 70%. That's not really how potential measurements work, especially in how we measure them here. So I would not go so far as say that coating the sample is better than coating the aggregates, just that both work to prevent the corrosion of the rebar. We got also some really interesting results when we added a bunch of sulfates in addition to the chlorides. So we have a very high probability of corrosion if we do nothing, that's expected. But then that probability doesn't really change if we coat the aggregates. And this was kind of surprising. And we did multiple runs because we didn't actually believe the results. And so what's happening here, we think, again, we're waiting for petrographic analysis. We think that sulfate is actually causing reacting with the silane in some way and causing some type of reaction to occur there. But if we coat the sample rather than the aggregates themselves, it seems like that is sufficient to prevent the initiation of corrosion. Now, I've was making these slides up and I forgot to put a little takeaways slide for the chemical part, but we actually explored delayed entry guide formation and some other aspects of chemical durability that aren't presented here. But the big takeaway is coating the aggregates with the silane has a tremendous benefit to the durability of the mixes. This could help, especially with recycled concrete fines, where we know it's contaminated, but we don't maybe know with what, or we just don't know what level. Hey, why not just throw some silane on there as we're mixing it? Could be a solution. All right, last little chunk, running out of time. Non-compliant gradations. Okay, I've talked with so many quarry operators and aggregate producers. They have a problem. They're making aggregates, either manufactured sands or fractionating some river sand, natural sand. Regardless of the process, they always have some type of, and I'll call it a byproduct, stuff that's okay. This is not what we need. So much so that several of the large aggregate manufacturers suppliers are trying to come up with names for this non-compliant sand to get people to use it in other applications. Like, they have so much of this. And so we're like, all right, how necessary are those C33 bounds? Because I have made concrete with C33 compliant sand and it was awful. It had horrible workability. So while the gradation is important, you can't just guarantee you'll get good stuff if you follow C33. So, like, how important are those bounds? And is it possible to make good concrete when we're outside the bounds and we still want, still do some testing? And the first thing is, well, does it meet specifications? Well, okay. DOTs are pretty conservative. Most DOTs say use C33 sand. That's it. Period. Can't change it. But if we look at ACI 318 for structural concrete, ooh, man, look at that. Aggregates shall, okay, got mandatory language, conform to C33, okay. But look, we have section B here. Aggregates that don't conform are permitted if they've been shown by tests and service to have adequate strength and durability. Interesting. So we actually had the ability, and maybe some of you, listening in have actually done this. We have the ability and have had it for a while to use non-compliant sands in structural concrete, but it has to be approved by someone. And which one of you are putting your stamp on that? So what are we going to do? Well, we were like, okay, one of the big issues is the strength and durability of this mix. And can we use plasticizers and, come up with workable, strong, durable mixes? And so we tested kind of three categories: compliant sands, but also sands that fell under the curve, so they were too coarse, or sands that were kind of above it and were too fine. Now, if you're really paying attention, I see there's 30 attendees, so we'll see who. This blue right here, I don't know if you can see my mouse, but the blue, it says compliant, but there's a nice little data point sticking outside the bounds there. So I left this in here because it's a great teaching thing, when I teach students. This came from our lab. That was the first delivery of sand we got for our concrete lab, where we called up the ready mix supplier and said, hey, please deliver, a truckload of your concrete sand. And they did that. And we ran a bunch of tests, as part of this project. And my PhD student had run the gradation analysis, but never looked at it and said, oh yeah, it's compliant because, the company delivered. Well, guess what? It wasn't. So we had to rerun all the testing. But I left this in here because I'm showing, like, you can't just assume it's compliant because it came from somewhere that's using it. This is more for student teaching. All right. So ACI 318 says adequate strength and durability. Well, let's just be good enough. We looked at a lot of things in this part of this study, but I'm just going to show very quickly drying shrinkage, compressive strength, and resistivity. So let's jump right into it. Look at this. The first non-compliant set of sands, which NC1, are the ones that were too fine. Okay, there's, drying shrinkage present, but we're pretty good if we're thinking about a bridge deck. We're still under that. NC2 is when the gradation was too coarse. We're still good. I mean, we got a lot of variability, though, in our measurements here. You see in both the too fine and too coarse, the error bar is pretty big. And then we have C, which is compliant, the real compliant, not the suspected compliant that I showed. And, we're meeting all the specs, but we got a much more consistent material, true, with the compliant sand. But we still made, in terms of drying shrinkage, a mix that would be okay to use. And then we look at compressive strength. Now this one was kind of interesting. So we look and see, again, our aggregates that are too fine. Okay, until we get to relatively high dosages of superplasticizer, we're actually not doing so well compared to the identical mix with a compliant aggregate up here. Okay, so we may suffer when the aggregate is too fine with our strength. When we're too coarse, we're better, but still, it's not meeting kind of the strength we would expect out of a compliant concrete mix. And that, it's kind of interesting. This necessarily wasn't the original reason why the ASTM committee came up with the bounds that they did for the C33. But okay, so strength could be affected, and even if we add a fair amount of plasticizers, that can help, but we're going to have to do other stuff. And what we did is, and this is a very extensive study, I'm only summarizing some of the results. We said, okay, the compliant mix had a water cement ratio of 0.42, even with high dosages of plasticizers at the same volumetrics, we're not getting the same strength. What if we drop the water cement ratio a little while maintaining workability and flowability of the mix using the appropriate amount of plasticizing agent? And we see with the fine aggregates, we're getting there still, but when we have a gradation that's too coarse, we can easily overcome the strength reduction. So we need the plasticizers to maintain the same equivalent workability of our mix, but we can actually get even stronger concrete than the target by reducing that water cement ratio. Yes, of course, you reduce water cement ratio, you get stronger concrete. That's known. But the question that was unknown, and actually it's real, you can't even find literature on this, is can you do it with non-compliant aggregate? And the answer is yes. Not so great when it's too fine. Yes, when we have it coarser. And then the surface resistivity, mainly to give some indication of durability. I don't have a lot of time to go through this, but basically the higher the number, the better your concrete is because it's less porous, it has a higher formation factor, all this sort of stuff. So we want big numbers. Great. Compliant mix, our baseline starts here. Ooh, our fine mix, not so good. Our coarse mix, it's too coarse. We're in the same ballpark, and statistically, it's almost the same, regardless of plasticizing dosage. So, kind of a takeaway here, and I'm summarizing a lot of work in a very short amount of time. Non-compliant sands can and should be used, with testing. The strength, especially when the non-compliancy is due to it being too coarse, can readily be met with some admixtures and just some tweaking of the mixture. And our durability, the resistivity measurement and some other durability testing that we did, that really gets in, it's more sensitive, I would say, to the non-compliantness of the aggregate source. When we start getting way too fine, we're going to run into some issues. And maybe even some of you have seen this with bleeding, and other stuff. Like, we did a lot of testing, so I haven't presented everything here. But huge takeaway, we should and can use non-compliant sands with testing. And it is preferred if they're a little coarser, they're on the coarser side of non-compliance than on the finer side. Okay. Oh my gosh. I'm running out of time here. Non-compliant is relative. What is non-compliant? It's just thresholds and specifications we came up with. In some cases, have been in place for decades with no one ever really looking at them. We have a bunch of chemical admixtures that are out there. We went over two of them, silanes and plasticizers, which are fairly common and commercially available. We have some tools and testing methodologies to kind of see, like, okay, is this acceptable or not? We should be thinking of more creative solutions. Like, you can be honest. You probably thought I was crazy when I said we were going to spray aggregates with silane and then mix concrete with it. I've gotten lots of reactions like that, but it works. Not saying it's super practical in all situations, but it is a solution that can help us, because there's no single answer to making us have more sand available to us. We're running out of compliant sands. We're going to have to start thinking of some more solutions. And one of those could be coating some aggregates with some silane. All right. I'll leave this up, but I just want to tell this very short story. So Federal Highway came out with a call a couple months ago about using or requesting proposals for business economic development on big ideas to solve problems in transportation. So I was like, hey, let's send them an email and say I have a solution to ASR, and that's literally what I put in the subject line, knowing at least they would read my email. I said, we'll spray the aggregates with silane. Yeah, they didn't really like that idea, but it got them thinking. They didn't say it was crazy. They just didn't think at this time it'd be practical. But sometimes the ideas start like that. And yeah, so I'll be able to answer any questions people might have.
Yeah, thank you, Armin, for delivering an outstanding presentation. And you really compiled everything together. Like, maybe it's a lot of work and all the results. It was a challenging job and you did it well. So thank you so much for that. And yeah, let's move to our question answer session. So how is it determined that the coating that is applied to potentially reactive aggregates is applied consistently and reliably from project to project?
Okay, so I'll first describe how we did it in the lab, and then I will propose how it may be able to be done in practice. So in the lab, we would weigh out the sand that we would be using for that mix. We would then, having calculated or estimated the surface area, say, okay, we need, I'm just saying, 67 milliliters of silane to coat the sand we have. And in a metal bowl, so it wouldn't absorb into anything, we would take that, pour it, stir it, and it very well, evenly coats everything. And we would initially kind of spread it out to make sure everything kind of was, coated. So in the lab, we have a process down that works pretty well. In practice, so you got tons, literal tons of sand, like kind of flying on the conveyor belt, going into the central mixer or just straight into the truck. How are you going to coat that? I mentioned asphalt. So the asphalt industry now, and I know they mix differently, but one of the things they do is they have admixture delivery systems that actually can coat the aggregates as they go into the heated drum. I'm not saying, concrete ready mix plants already have this in place. Probably no one does. I'm just indicating that the technology is out there and it would be possible, but obviously a significant capital expense for a plant to add that. Um, I'm not even going to really propose this, but it's also possible because my student tried it on a small sample. The silane we have drains down pretty well. So it is possible to spray kind of like a stockpile and it will drain through it. But I'd be very hesitant to recommend that as a process. Those stockpiles at ready-mix plants get really big.
Mm-hmm. Yeah, so for this question, there is again a follow-up sentence. How is this coating tested, and how often should it be tested to assure consistent performance throughout the project?
Okay, so we never measured the thickness on a sand particle. It'd be actually very challenging to do that because the thickness is expected to be very thin. Now, monitoring the progress throughout a project, that we hadn't really looked at in this study. I'll just throw some ideas out there that revolve around taking samples of, like, let's say you just, take a sample off the conveyor belt of already treated sand, coated sand. It would probably be pretty easy to do some type of 24-hour water absorption test with that sand. Like, you weigh the sand, toss it in a beaker of water, let it sit 24 hours, take it out. Theoretically, it should absorb no water because it's been coated, and you could probably come up with some type of index from that to get a ballpark of the efficiency of the coating in practice.
So to some extent, it could be also like project to project. I mean,
Yeah.
So our next question is, how does coating the aggregate with silane affect the interfacial transition zone thickness and strength?
Okay, so I mentioned we have pending petrographic analysis. I am certainly not qualified to perform petrography. No one on campus is. So we are sending it out to a firm, a private entity that has very well experienced petrographers. I don't have an answer yet as to what the ITZ is doing. I have jokingly told someone else, and just please, this is more of a joke. You saw from my slides, I like, not being as serious. I jokingly told them there is no ITZ, so we have amazing concrete because there's no transition. It's the paste, the silane, and then the aggregate. They don't see each other. There's no ITZ. We solved the problem. That's not my serious professional opinion, but what I think is going to happen is we'll see some type of ITZ-like region. It just won't present itself in the traditional way. And that's probably the cause of the decrease in strength that we see.
Okay, great. Thank you. Our next question is there a past history on the performance of coating aggregates that the industry can reference to help gain owner confidence that coated aggregates will perform well over the service life?
Unfortunately, as far as we can tell, and I will love you guys sending me anything refuting this, we have only been able to find one research publication worldwide where they took silane, coated aggregates, and then mixed concrete with it. No one, at least publication-wise, has seemed to have tried this before. So to answer the question, no, we don't have long-term data. What we can say is with the autoclave test, which is obviously not long-term, but very extreme environment, the material the silane, the coating, seemed to still remain intact. Now, that doesn't mean it would last 5 years, 10 years, 20 years. We can't say, but we can say it's not easily damaged or easily degraded. So, but we're
Yeah.
going to keep some of the specimens we have from the study in buckets of solution for years and just kind of check on them. So maybe in 5 years, find me at ACI and ask how
Hmm.
the silane
Yeah,
project's going.
that could be another project where you can write a guideline and like on the performance based history. Hmm. Okay. And our last question is, can you blend aggregate sources with non-compliant aggregates, some chemically coated and some without chemical coating, to dilute the amount of aggregates that are reactive to ASR, for instance?
Yes. So I think, and can't remember the name. I recall reading a paper too, especially because you mentioned ASR, where they did that. They said, okay, it's really bad, 100%, let's say ASR active sand, because that causes expansion everywhere. But concrete is pretty strong, so if it's only expanding in a little bit of it, it may still be able to withstand that internal stress and not crack.
Mhm.
So very briefly, yes, I think you could dilute the badness of ASR with using a known non-reactive sand to help spread out that and not have it generate such high internal stresses. I don't think that behavior would be very linear, like saying, oh, I'll reduce expansion by 50% if I blend it 50%. I don't think it'll work like that, but I think you would be able to uh, reduce, the cracking potential you would see in that. Um,
Mhm. Yeah, no, thank you. You answered it well. So thank you so much. With this, we end our question answer session. Thank you, Armin, for outstanding presentation. Before we go, I have few announcements. So I hope you see my screen. Yeah. So Next is organizing 2 full-day webinars, one on structural rehabilitation and strengthening using FRP composites in mid-September. And the another one is on advancement in polymer utilization in 3D printing construction industry, which will be in mid-October. So if any of these topics are of your interest, please submit an abstract of up to 300 words, including the duration of your presentation, and please send it to info@nonmetallic.org. And this is the list of our upcoming webinars at ACI University. Please visit aciuniversity.com to register. With this, we are at the end of our webinar. Thank you all. Thank you, Armin. Thank you all the participants for joining today's webinar. See you all again for next month for our next webinar. Thank you.